You have been lied to about the deadliest object in space. Every documentary, every article, every science channel tells you the same story. Black holes are the ultimate cosmic killers. Gravity so strong that nothing escapes. Event horizons where physics breaks down. The universe's final executioner. Wrong. There is something worse. An object so violent that it can kill you from 10 light years away. So magnetic that it bends the laws of quantum mechanics. So unstable that it erupts without warning in explosions that flood entire star systems with lethal radiation. It is called a magnetar, and it makes black holes look predictable. A magnetar at half the distance to the moon would rip the iron from your blood through magnetic force alone. A starquake on its surface, a fracture less than a millimeter wide, releases more energy than the sun produces in 100,000 years. In December 2004, a magnetar 20,000 light-years away erupted and measurably damaged Earth's atmosphere. 20,000 light-years. A black hole at that distance would not even register. If you want to understand why the most dangerous object in the universe is not what you think, hit that like button and subscribe. This is the truth about cosmic threats that nobody talks about. Prepare yourselves. We begin. Most people have never heard the word magnetar. It does not appear in school textbooks. It rarely makes headlines. But among astrophysicists, the term carries a weight that few other cosmic objects can match. A magnetar is a neutron star, but not just any neutron star. It is a neutron star that has gone wrong in the most spectacular way physics allows. When a massive star runs out of fuel, its core collapses. The outer layers explode in a supernova, but the core keeps falling inward, compressing matter to densities that should not exist. Protons and electrons are crushed together, forced to merge into neutrons. What remains is a sphere roughly 20 kilometers across, containing more mass than the entire Sun. A single teaspoon of neutron star material weighs as much as Mount Everest. This is already extreme, but magnetars take it further. During the collapse, the star's magnetic field gets compressed along with everything else. Magnetic field lines that once stretched across millions of kilometers are suddenly confined to a sphere the size of a city. The field strength does not just increase, it explodes. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar's field is 1,000 times stronger than that. 1 quadrillion times Earth's magnetic field strength, concentrated into an object you could drive across in half an hour. At this field strength, physics stops behaving the way you learned in school. Atoms become elongated, stretched into needle shapes by magnetic forces. The empty space between particles, the quantum vacuum itself, begins to act like a solid material. Photons travelling through this magnetized void split into 2 separate light rays, each following different rules. The magnetic field is so powerful that it warps the structure of space-time, creating gravitational effects independent of the neutron star's mass. But the most disturbing property of a magnetar is not its magnetic field strength. It is what that field does to the star itself. Neutron stars are unimaginably dense, but they still have a crust, a solid outer layer made of atomic nuclei crushed into a crystalline lattice. The magnetar's field is so intense that it physically stresses this crust, bending and twisting it like a piece of metal in a vise. The crust resists, but only up to a point. Eventually it fractures. When that happens, the magnetar does not just crack, it erupts. The sudden shift in the crust releases magnetic energy that has been building for years, sometimes decades. This energy does not dissipate slowly. It explodes outward in a fraction of a second, creating a blast of gamma rays and X-rays that can be detected across the galaxy. These are called starquakes, and they are the reason magnetars are the most dangerous objects in the known universe. A black hole will kill you if you get too close. A magnetar will kill you from distances that should be safe. And the worst part is this. We have found roughly 30 confirmed magnetars in our galaxy so far. But models suggest there could be hundreds more, silent and hidden, waiting for the next starquake to announce their presence. We are living in a galaxy filled with magnetic landmines, and most of them have not gone off yet. The story of a magnetar begins with a star that should never have existed in the first place. Not every star can become a magnetar. The progenitor must be massive, at least 8 times the mass of the Sun, but not too massive. If the star exceeds a certain threshold, it collapses directly into a black hole, bypassing the neutron star phase entirely. The magnetar formation window is narrow, and the process is violent beyond comprehension. For millions of years, the massive star burns through its nuclear fuel in layers. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. The core grows hotter and denser, igniting heavier elements in sequence: carbon, neon, oxygen, silicon. Each stage burns faster than the last. The final silicon burning phase lasts only days. At the center of the star, an iron core forms, and iron cannot fuse. Iron is the end of the line. When the core reaches approximately 1.5 solar masses, electron degeneracy pressure can no longer support it. The core collapses. What happens next occurs in less than 1 second. The iron core implodes at nearly 1/4 the speed of light. Matter that occupied a volume the size of Earth compresses into a sphere 20 kilometers wide. The temperature spikes to 100 billion degrees. Protons and electrons are forced together by sheer pressure, merging into neutrons and releasing a flood of neutrinos. These ghostly particles carry away 99% of the collapse energy, streaming outward through the star at the speed of light. The collapse halts when neutron degeneracy pressure finally stops the infell. But the outer layers of the star are still falling inward, unaware that the core has already bounced. When the infalling material hits the newly formed neutron star, it rebounds in a shockwave that races back outward. This shockwave stalls almost immediately, choked by the dense overlying layers. Under normal circumstances, the supernova would fail. The star would collapse into a black hole without ever exploding, but the neutrinos save it. A tiny fraction of the neutrino flood, less than 1%, deposits energy into the stalled shockwave. This is enough. The shockwave revives and blasts outward, tearing through the star's outer layers at tens of thousands of kilometers per second. The star explodes in a Type II supernova, briefly outshining every other star in the galaxy combined. For a few weeks, a single dying star produces more light than 100 billion normal stars. But the real violence is not in the explosion. It is in what the explosion leaves behind. The neutron star at the center is spinning. During the collapse, conservation of angular momentum accelerates the core's rotation to absurd speeds. A star that once rotated once every few weeks now spins hundreds of times per second. The surface of the neutron star is moving at a significant fraction of the speed of light, and the magnetic field, compressed and amplified by the collapse, is now stronger than anything else in the universe. Not all neutron stars become magnetars. Most have magnetic fields around 1 trillion times Earth's strength, which is already extreme. But in rare cases, something goes wrong during the collapse. The exact mechanism is still debated, but the leading theory involves dynamo amplification during the first few seconds of the neutron star's life. Convection currents in the superheated neutron fluid, combined with rapid rotation, create a feedback loop that amplifies the magnetic field by a factor of 1,000 or more. The result is a magnetar, a cosmic aberration with a magnetic field so intense that it dominates every other force except gravity itself. The magnetic pressure inside the star is strong enough to deform the neutron star's shape, creating bulges and distortions in the crust. The field lines twist and tangle, storing enormous amounts of energy in configurations that are not stable. The magnetar is born already wounded, already stressed, already primed to erupt. And it does. Within the first few thousand years of its life, a magnetar experiences dozens or hundreds of starquakes as its crust adjusts to the relentless magnetic stress. Each quake releases energy equivalent to thousands of supernovae. But unlike a supernova, which happens once and then fades, a magnetar can erupt again and again, unpredictably, for tens of thousands of years. The birth of a magnetar is not a single event. It is the beginning of a reign of terror that lasts longer than human civilization. To understand why magnetars are more dangerous than black holes, you need to understand what a magnetic field of this strength actually does. Numbers alone do not convey the horror. A magnetar's surface magnetic field reaches 10 to the 15th Gauss, 1 quadrillion times stronger than Earth's field. This is not just strong, this is a regime where the rules change. At 1,000 kilometers from a magnetar, the magnetic field strength is still around 1 billion Gauss. This is where things stop making sense. If you were somehow placed at this distance, protected from the radiation and heat, the magnetic field alone would kill you in seconds. Not through any mechanical force you could see or feel, but through quantum effects operating at the atomic level. Your body contains iron. Hemoglobin molecules in your blood carry iron atoms that bind oxygen for transport to your cells. In a normal magnetic field, even a strong one, these iron atoms experience a tiny attractive force. In a magnetar's field, the force becomes lethal. The magnetic field gradient is so steep that it creates differential forces across the length of a single molecule. The iron atoms in your hemoglobin would be ripped out of their molecular bonds and pulled toward the magnetar. Your blood would cease to function as blood. You would suffocate at the cellular level, while your cardiovascular system tore itself apart from the inside. But it gets worse. The magnetic field does not just affect iron. At field strengths above 1 billion Gauss, all atoms become magnetically responsive. Electrons in their orbital shells are forced into elongated configurations, stretched along the direction of the magnetic field. Atoms that are normally spherical become cigar-shaped. Chemical bonds which depend on precise electron orbital geometries break down. Water molecules cannot maintain their structure. Proteins unfold. DNA strands snap. The molecular machinery of life disintegrates because the magnetic field has fundamentally altered the quantum mechanics that allow chemistry to exist. This is not speculation. This is established physics, confirmed by laboratory experiments at lower field strengths and extrapolated through quantum electrodynamics to magnetar levels. At 1,000 kilometers from a magnetar, you do not die from radiation or heat. You die because the atoms in your body stop being atoms in any recognizable sense. But the magnetic field does something even stranger to empty space itself. According to quantum field theory, the vacuum is not truly empty. It seethes with virtual particle pairs, electrons and positrons that pop into existence for infinitesimal fractions of a second before annihilating each other. These quantum fluctuations are normally invisible, contributing only to subtle effects that require sensitive instruments to detect. In a magnetar's field, the vacuum changes. The virtual particle pairs become polarized, aligned with the magnetic field direction. This polarization gives the vacuum optical properties. Empty space near a magnetar behaves like a birefringent crystal, the kind used in polarized sunglasses. Light passing through this magnetized vacuum splits into two rays with different polarizations, traveling at slightly different speeds. This effect is called vacuum birefringence, and it was predicted by quantum electrodynamics in the 1930s. For decades, it remained theoretical because no laboratory could generate magnetic fields strong enough to test it. Then, astronomers found magnetars. In 2016, a team using the Very Large Telescope in Chile detected vacuum birefringence around a magnetar for the first time. The empty space around the neutron star was measurably polarizing light, exactly as the equations predicted. This confirmed something terrifying. Magnetars do not just warp space-time through gravity, like black holes do. They warp the quantum vacuum itself, altering the fundamental properties of empty space across thousands of kilometers. The region around a magnetar is not normal space. It is a zone where quantum field theory operates in a regime that exists nowhere else in the observable universe. The magnetic field also creates another effect that sets magnetars apart from every other cosmic object: magnetic pressure. In normal astrophysics, pressure comes from particles colliding, from heat and motion. But magnetic fields exert their own pressure, independent of temperature or particle density. At magnetar field strengths, magnetic pressure becomes a dominant force, comparable to the gravitational pressure trying to crush the neutron star inward. This magnetic pressure deforms the neutron star itself. The star is no longer perfectly spherical. It bulges along the magnetic axis, creating an oblate shape. The crust, already under immense stress from the star's gravity, now experiences additional strain from the magnetic field trying to twist and bend it. This is why magnetars have starquakes. The crust is caught between gravitational compression and magnetic distortion, and eventually something has to give. When the crust fractures, the magnetic field lines snap and reconnect in new configurations, releasing energy that has been stored in the magnetic field topology. This is not a thermal process. It is pure magnetic energy converting directly into electromagnetic radiation. The gamma rays and X-rays that blast outward from a starquake carry energies that dwarf anything a chemical or even nuclear explosion could produce. A single starquake releases more energy in 1/10 of a second than the Sun will produce in 100,000 years. And here is the critical difference between a magnetar and a black hole. A black hole's danger is localized. The event horizon is the point of no return, and it has a finite size. Get far enough away, and you are safe. Orbit at a stable distance, and you can stay there indefinitely. A black hole is predictable. Its gravity follows the mathematics of general relativity with precision. A magnetar is not predictable. Its magnetic field extends across thousands of kilometers, warping space and vacuum in ways that make survival impossible. Its starquakes happen without warning, following no pattern that astronomers have been able to detect. And the radiation from those starquakes travels outward at the speed of light, flooding entire star systems with lethal doses of gamma rays and X-rays. You cannot see it coming. By the time you detect the burst, you're already dead. A starquake sounds almost benign. The word suggests something geological, something you might feel as a tremor if you were standing on the surface. This is a catastrophic failure of language. A magnetar starquake is one of the most violent events in the universe, and it happens on an object where the surface gravity is 200 billion times stronger than Earth's. The neutron star's crust is not like Earth's crust. It is a crystalline lattice of atomic nuclei, mostly iron, crushed together at densities where the spaces between atoms have collapsed. The nuclei are packed so tightly that they form a solid structure stronger than any material that exists on Earth. Steel has a tensile strength of around 500 million pascals. Neutron star crust has a tensile strength estimated at 10 to the 30th pascals. It is the strongest solid in the universe, but even this material has limits. The magnetar's field is constantly evolving, twisting and writhing as currents flow through the neutron star's interior. These currents create magnetic stresses in the crust, bending it, warping it, loading it with strain energy. For years, sometimes decades, the crust resists. The crystalline lattice holds, but the stress keeps building. When the crust finally fails, it does not crack slowly. The fracture propagates, racing across the neutron star's surface in milliseconds. The crust shifts by less than 1 millimeter. On a human scale, this is nothing. On a neutron star, where gravity is so strong that a millimeter represents an enormous amount of gravitational potential energy, this shift releases power beyond comprehension. The numbers are difficult to grasp, so consider this. The Sun produces 3.8 times 10 to the 26th watts of power. It does this continuously, fusing hydrogen into helium at a rate of 600 million tons per second. The Sun has been doing this for 4.5 billion years, and it will continue for another 5 billion. The total energy output of the Sun over 100,000 years is approximately 10 to the 41 joules. A major magnetar starquake releases 10 to the 46 joules in 1/10 of a second. That is 100,000 times the Sun's century-long output, compressed into a fraction of a human heartbeat. The energy does not come from nuclear reactions or gravitational collapse. It comes from the magnetic field itself, from the topology of field lines snapping and reconnecting as the crust shifts. This energy emerges as electromagnetic radiation. Gamma rays and X-rays blast outward from the magnetar's surface in a directed beam that sweeps across space like a cosmic searchlight. If that beam points toward your star system, everything in its path is sterilized. The radiation flux is intense enough to ionize atmospheres, strip away ozone layers, and deliver lethal doses to any life form on any planet within the beam's reach. We know this because it has already happened. On December 27, 2004, astronomers detected an event that redefined our understanding of magnetar violence. The magnetar SGR 1806-20, located roughly 50,000 light-years away on the far side of the Milky Way, experienced a starquake. The gamma-ray burst that followed was the brightest event ever recorded from beyond our solar system. The burst lasted 1/10 of a second. In that brief flash, the magnetar released 50,000 years. The radiation travelled across the galaxy at light speed, a sphere of gamma rays expanding outward in all directions. 50,000 years after the starquake occurred, that sphere reached Earth. Even at 50,000 light-years distance, the effects were measurable. The gamma rays hit Earth's upper atmosphere and ionized the particles there, disrupting the ionosphere's normal structure. Radio communications were affected, satellites detected the surge, scientific instruments around the world recorded the event, and for several minutes, astronomers watched as a magnetar halfway across the galaxy reached out and touched our planet's atmosphere. The radiation dose Earth received was harmless. We are protected by our atmosphere and magnetic field, and the distance was enormous. But the implications were clear. If that magnetar had been closer, the starquake would have been catastrophic. At 10 light-years distance, the same burst would have delivered a radiation dose comparable to standing next to an unshielded nuclear reactor. Ozone depletion would have been immediate and severe. The food chain would have collapsed within months. Mass extinction would have followed. And here is the truly disturbing part. The December 2004 event was not unique. Magnetars experience starquakes regularly throughout their lifetimes. Smaller quakes happen every few years. Major eruptions occur every few decades. The magnetar that hit Earth's atmosphere in 2004 has erupted multiple times since then, each event recorded by X-ray and gamma-ray telescopes in orbit. Astronomers have catalogued dozens of these bursts from different magnetars scattered across the galaxy. Each one represents a moment when a neutron star's crust fractured and released magnetic energy in a blast that could be seen across thousands of light-years. The bursts follow no predictable pattern. They are not periodic like pulsar emissions. They are chaotic, driven by the internal evolution of the magnetic field, which operates on timescales we cannot model accurately. This unpredictability is what makes magnetars more dangerous than black holes. A black hole's gravity is constant. You can calculate orbital paths with precision. You know where the event horizon is, and you can avoid it. A magnetar can be quiet for decades, appearing dormant, and then without warning, it erupts. The gamma-ray burst travels at light speed. There is no advance warning, no time to evacuate, no way to shield yourself if you are in the beam's path. The magnetar's danger radius is not defined by an event horizon. It is defined by how far its gamma-ray burst can deliver lethal radiation doses. For a major starquake, that radius extends across dozens of light-years. A magnetar does not need to be close to kill you. It just needs to be pointing in your direction when it decides to erupt. The fundamental difference between a black hole and a magnetar comes down to range. A black hole's lethality is confined to a relatively small region of space. The event horizon of a stellar mass black hole, the kind formed from a collapsed star, has a radius of only a few kilometers. Even the tidal forces that shred matter before it reaches the event horizon operate over distances measured in hundreds or thousands of kilometers. If you maintain a safe orbital distance from a black hole, you can remain there indefinitely. The danger is predictable. The gravitational field follows precise mathematical rules. You can calculate exactly where the point of no return exists, and as long as you stay outside that boundary, the black hole cannot harm you. It cannot reach out across space and strike you down. Its influence diminishes with distance according to the inverse square law, just like any gravitational field. A magnetar operates under completely different rules. Its magnetic field extends thousands of kilometers from the surface, creating a zone where quantum mechanics breaks down and atoms cannot maintain their normal structure. But the magnetic field is not even the primary threat. The real danger is the electromagnetic radiation released during starquakes. Gamma rays and X-rays do not obey an inverse square law in the same way gravity does. They travel in beams, focused by the magnetar's magnetic field geometry into directed streams that can maintain lethal intensity across vast distances. When a magnetar erupts, it does not radiate energy equally in all directions. The emission is concentrated along the magnetic axis, creating searchlight beams of hard radiation that sweep through space as the magnetar rotates. If you're caught in one of these beams, distance provides less protection than you might expect. The December 2004 event demonstrated this clearly. At 50,000 light-years, the gamma-ray burst was still strong enough to measurably affect Earth's ionosphere. At closer distances, the effects would scale accordingly. Astrophysicists have calculated the lethal radius for various magnetar events. For a typical starquake, the kind that happens every few decades, the danger zone extends roughly 10 light-years from the magnetar. Within this radius, a planet in the beam's path would receive a radiation dose sufficient to cause immediate ecological collapse. The ozone layer would be stripped away. Ultraviolet radiation from the host star would flood the surface. Photosynthesis would fail in the oceans. The base of the food chain would disintegrate. For a giant flare, the kind of extreme event that happens perhaps once or twice in a magnetar's lifetime, the lethal radius extends even farther. The December 2004 burst was a giant flare. If that magnetar had been located 10 light-years from Earth instead of 50,000, the radiation dose would have been 25 million times stronger. Every living thing on Earth's surface would have been exposed to radiation levels comparable to standing at ground zero of a nuclear detonation. The atmosphere would have absorbed some of the gamma rays, but in doing so, it would have been chemically altered. Nitrogen and oxygen molecules would have been split apart by the high-energy photons, recombining into nitrogen oxides. These compounds would have rained down as acid, poisoning water supplies and soil. The ozone layer would have been destroyed completely, and it would have taken decades to recover if it recovered at all. Compare this to a black hole at the same distance. A stellar mass black hole 10 light-years from Earth would have no measurable effect on our planet. Its gravity would be too weak at that distance to influence Earth's orbit. It would emit no radiation unless it was actively feeding on matter, and even then, the accretion disk's radiation would be far less intense than a magnetar's starquake. You could point a telescope at it and observe it safely. You could send a probe to study it. The black hole would be an object of scientific curiosity, not an existential threat. The magnetar at 10 light-years would be a sword hanging over your civilization. You would live in constant awareness that at any moment, without warning, the magnetar could erupt and end everything. There would be no defense, no way to predict when the next starquake would occur. No technology capable of shielding an entire planet from a gamma-ray burst of that magnitude. This is why the claim that black holes are the universe's ultimate killers is wrong. Black holes are dangerous if you approach them. Magnetars are dangerous if they exist anywhere in your stellar neighborhood. The threat radius is thousands of times larger. The danger is active rather than passive. A black hole sits in space waiting for matter to fall into it. A magnetar hunts. And we are not safe simply because no known magnetar exists within 10 light-years of Earth. Our knowledge of magnetar locations is incomplete. These objects are difficult to detect unless they are actively erupting. A dormant magnetar, one that has not experienced a major starquake in centuries, would be nearly invisible to current telescopes. It would appear as nothing more than a faint X-ray source, easily overlooked among the thousands of other X-ray emitting objects scattered across the sky. Astronomers estimate that our galaxy contains at least 30 million neutron stars, the remnants of every massive star that has died in the Milky Way's 10 billion-year history. Of those 30 million, perhaps 10,000 are magnetars, born with the extreme magnetic fields that define this class of object. We have confirmed the existence of only 30 magnetars so far. That means we have found 0.3% of them. The other 99.7% are out there somewhere, hidden in the darkness between stars. Some are erupting regularly, broadcasting their presence through gamma-ray bursts that we have not yet detected. Others are dormant, their crusts temporarily stable, their magnetic fields quietly evolving toward the next fracture. Any one of them could be within lethal range of Earth, and we would not know until it erupted. A black hole gives you certainty. You can see its effects on surrounding matter. You can map its location precisely. You know where the danger gives you uncertainty. You do not know where all of them are. You do not know when they will erupt. And you cannot avoid something you cannot see coming. The magnetar catalogue is small, but every entry represents a confirmed cosmic threat. Astronomers have identified roughly 30 magnetars in the Milky Way, each one a neutron star with a magnetic field strong enough to qualify it as a distinct class of object. These are not hypothetical. They are real, observable, and in some cases disturbingly active. The first magnetar was discovered in 1979, though astronomers did not understand what they were looking at the time. On March 5th of that year, satellites orbiting Earth detected a massive gamma-ray burst originating from the constellation Dorado. The burst lasted only a fraction of a second, but it was so intense that it saturated detectors, overloaded instruments, and left scientists scrambling to explain what could produce such an extreme event. The source was eventually identified as SGR 0526-66, a neutron star located in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of 160,000 light-years. The fact that a gamma-ray burst could be detected across that distance indicated an energy release far beyond anything known at the time. It took years of theoretical work before astrophysicists developed the magnetar model to explain what they had observed. Since then, the catalogue has grown slowly. Magnetars are rare, and they are difficult to detect unless they happen to be erupting when we are looking in their direction. Most known magnetars were discovered through X-ray observations, identified as unusually bright and variable X-ray sources that did not fit the profiles of other neutron star types. The closest known magnetar to Earth is 1E1848-0145, located approximately 9,000 light-years away in the constellation Aquila. This is far enough that a starquake would not pose an immediate threat to Earth, but close enough that the object has been studied extensively. Observations show that it rotates once every 11 seconds, unusually slow for a neutron star, and that its X-ray emissions vary unpredictably over timescales ranging from hours to years. The most powerful known magnetar is Swift J 182 2.3-1606, discovered in 2011. This object holds the record for the strongest magnetic field ever measured, estimated at nearly 10 to the 16th Gauss at the surface. It is located roughly 16,000 light-years from Earth, deep within the Milky Way's disk. When it was first detected, it was erupting in a series of X-ray bursts that lasted for months, each burst releasing energy equivalent to what the Sun produces in years. Then there is SGR 1806-20, the magnetar responsible for the December 2004 giant flare that affected Earth's ionosphere. This object is located on the opposite side of the galaxy, roughly 50,000 light-years away, yet its eruption was powerful enough to be detected and measured by instruments all over the planet. Follow-up observations revealed that the magnetar rotates once every 7.5 seconds and has experienced multiple smaller eruptions since the giant flare. Another notable entry is 4U0142+61, located about 13,000 light-years away in the constellation Cassiopeia. This magnetar is embedded in a supernova remnant, the expanding shell of debris left over from the star that exploded to create it. The remnant is roughly 3,000 years old, which means the magnetar itself is 3,000 years old, still in the violent early phase of its existence when starquakes are most frequent. What makes the catalogue truly disturbing is not the objects we have found, but the ones we have not. Statistical models based on supernova rates and stellar population dynamics suggest that the Milky Way should contain between 10,000 and 100,000 magnetars. We have confirmed 30. That leaves thousands of these objects unaccounted for, scattered throughout the galaxy in locations we have not surveyed or in states where they are not currently emitting enough radiation to be detected. Some magnetars go dormant. Their magnetic fields remain intense, but their crusts stabilize temporarily, and the starquakes stop. These dormant magnetars emit only faint X-rays from their cooling surfaces, making them nearly impossible to distinguish from ordinary neutron stars unless you measure their magnetic fields directly, which requires detecting specific spectral features that are only visible during certain emission states. This means there could be a dormant magnetar within 10 light-years of Earth right now, and we would not know. It would not show up in X-ray surveys as anything unusual. It would not be erupting, it would simply be there, waiting for its crust to fracture again, waiting for the magnetic stress to build to the breaking point. The galactic distribution of known magnetars shows no clear pattern. They are found in the spiral arms, in the galactic disk, and even above and below the plane of the galaxy where stellar density is lower. Some are isolated, drifting through space far from any other stars. Others are located in dense star-forming regions where massive stars are still being born. The randomness of their distribution suggests that magnetar formation is not confined to specific galactic environments. It can happen anywhere a massive star dies, and they are not all the same. Magnetars show a wide range of behaviors and properties. Some rotate rapidly, spinning dozens of times per second. Others rotate slowly, taking 10 seconds or more to complete a single rotation. Some erupt frequently, producing dozens of small bursts per year. Others remain quiet for decades between major flares. The diversity suggests that magnetar evolution is complex, influenced by factors we do not fully understand. One of the most mysterious magnetars is SGR 0501+4516, located roughly 15,000 light-years away. This object has displayed bursting behavior that defies easy explanation. In 2008, it suddenly became active, producing hundreds of X-ray bursts over the course of several months before returning to quiescence. Then, in 2015, it erupted again, this time with a different burst pattern. The irregularity suggests that the internal magnetic field configuration is evolving in ways that make the star's behavior fundamentally unpredictable. Astronomers continue to search for more magnetars, using X-ray telescopes and gamma-ray detectors to scan the sky for the characteristic emission signatures. Each new discovery adds another data point, another object to study, another confirmed threat lurking in the galactic darkness. But the searches also reveal how much we are missing. For every magnetar we find, there are hundreds or thousands more that remain invisible, hidden by distance, orientation, or dormancy. The Magnetar Zoo is not a collection of curiosities. It is a roster of the galaxy's most dangerous objects, and we have only just begun to take attendance. The magnetic field of a magnetar does not just affect matter, it affects the structure of reality itself at the quantum level. This is not metaphor or exaggeration. This is confirmed physics, observed and measured in the radiation coming from these objects. At field strengths exceeding 1 billion Gauss, quantum electrodynamics predicts that the vacuum undergoes a phase transition, acquiring properties that do not exist in normal space. Empty space, according to quantum field theory, is not empty. It is filled with virtual particles, fleeting fluctuations in the quantum fields that permeate the universe. Electron-positron pairs blink into existence for immeasurably brief moments before annihilating each other and vanishing back into the vacuum. Under normal conditions, these fluctuations average out to zero. They contribute nothing to the macroscopic properties of space. You cannot see them or measure them directly. But in a magnetar's field, the virtual particles do not average out to zero. The magnetic field polarizes them, aligning the virtual electrons and positrons along the field direction. This polarization gives the vacuum a preferred orientation, breaking the isotropy that normally characterizes empty space. Space near a magnetar has a grain, like wood or fabric. Photons traveling through this polarized vacuum experience different refractive indices depending on their polarization state. This is vacuum birefringence. Light splits into two rays, one polarized parallel to the magnetic field and one perpendicular to it. The two rays travel at slightly different speeds, accumulating a phase difference as they propagate. If you could observe a star through the magnetized vacuum surrounding a magnetar, you would see two images of that star slightly offset from each other, each with a different polarization. For decades, this effect remained theoretical. Laboratory magnetic fields, even the strongest ever produced, fall short of the critical threshold by factors of millions. No terrestrial experiment could generate fields strong enough to polarize the vacuum. Magnetars provided the only natural laboratory where the effect could occur. In 2016, astronomers using the Very Large Telescope in Chile observed the magnetar RxJ 185 6.5-3754 and measured the polarization of light coming from its surface. The data showed exactly what quantum electrodynamics predicted. The light was linearly polarized to a degree that could only be explained by vacuum birefringence. The empty space around the magnetar was acting as a polarizing filter, imprinting its structure onto the radiation passing through it. This was the first direct observational confirmation that magnetars warp the quantum vacuum. The vacuum near these objects is not the same as the vacuum everywhere else in the universe. It has measurable optical properties. It bends light not through gravity, but through quantum field effects that emerge only at extreme magnetic field strengths. But vacuum birefringence is not the only quantum effect operating near magnetars. At even higher field strengths, closer to the neutron star's surface, quantum electrodynamics predicts that photons can split into electron-positron pairs. This process, called photon splitting, occurs when a high-energy gamma-ray photon travels through the magnetized vacuum and decays into a real electron and positron rather than virtual ones. Under normal conditions, photons cannot decay into particle pairs unless they interact with matter or another photon. Energy and momentum conservation forbid it. But in a magnetar's field, the vacuum itself provides the necessary interaction. The magnetic field modifies the dispersion relation for photons, allowing decay channels that would otherwise be forbidden. Gamma rays produced in the magnetar's magnetosphere can split into particle pairs before they escape into interstellar space. This creates a particle wind around the magnetar, a flow of electrons and positrons streaming outward from the star's surface. These particles are not products of nuclear reactions or thermal processes. They are created directly from the electromagnetic field by quantum effects that operate only in the most extreme magnetic environments in the universe. The particle wind interacts with the magnetar's magnetic field, creating a magnetosphere far more complex than anything found around ordinary neutron stars. Currents flow through this magnetosphere, twisting the magnetic field lines into intricate topologies that store enormous amounts of energy. When the magnetar's crust shifts during a starquake, these field lines snap and reconnect, releasing the stored energy and the gamma-ray bursts that make magnetars so dangerous. Another quantum effect predicted to occur near magnetars is the modification of electron energy levels in atoms. In a normal magnetic field, electron orbitals experience Zeeman splitting, a small shift in energy levels that causes spectral lines to split into multiple components. In a magnetar's field, the splitting becomes so extreme that the entire atomic structure is altered. Atoms become elongated, stretched into cylindrical shapes along the magnetic field direction. The electron orbitals that are normally spherical or dumbbell-shaped become needle-like. Chemical bonds, which depend on the overlap of electron orbitals between atoms, can no longer form in the usual way. The chemistry near a magnetar's surface operates under rules that do not apply anywhere else. Hydrogen, the simplest atom, provides the clearest example. In a magnetar's field, the hydrogen atom's ground state energy shifts by an amount comparable to the atom's binding energy. The electron is squeezed closer to the proton along the field direction and stretched outward perpendicular to it. At the highest field strengths, near 10 to the 15th Gauss, the atom becomes so distorted that it barely resembles hydrogen anymore. Iron atoms, which form the crystalline lattice of the neutron star's crust, experience even more dramatic effects. Iron has 26 electrons arranged in multiple shells. In a magnetar's field, all of these electrons are forced into configurations that minimize their magnetic energy. The atom collapses along the field direction, becoming a thin needle of electron probability. The chemical properties of iron, its ability to form metallic bonds and conduct electricity, change completely. This is why the neutron star crust behaves the way it does. The material is not just compressed by gravity, it is magnetically constrained, locked into structures that can only exist in these extreme field environments. When the crust fractures during a starquake, it is not just a mechanical failure, it is a quantum phase transition, a restructuring of matter at the atomic level, as magnetic stresses overcome the forces holding the crystalline lattice together. The quantum effects near magnetars also include modifications to fundamental constants. The fine structure constant, which governs the strength of electromagnetic interactions, appears to vary in strong magnetic fields. This variation is tiny, but it is measurable in principle. If confirmed, it would indicate that the laws of physics themselves are not absolute, but depend on the local field environment. Magnetars are laboratories for physics that cannot be replicated anywhere else. They push quantum electrodynamics into regimes where perturbation theory breaks down, and where calculations require methods that are still being developed. Every observation of magnetar radiation provides data that tests our understanding of how quantum fields behave under extreme conditions, and every test reveals that the universe is stranger than our equations suggest. The quantum vacuum is not inert. Space itself has structure that emerges when magnetic fields reach strengths that dwarf anything we can create artificially. Magnetars are not just dangerous because of their radiation, they are dangerous because they reveal that reality is more fragile and more malleable than we assumed. The rules can change, the vacuum can polarize, atoms can be reshaped, and all of it happens in a region of space surrounding an object the size of a city. When a massive star collapses into a magnetar, it does not do so in isolation. Most massive stars exist in systems with companion stars, and many have planets orbiting them. The supernova that birthed the magnetar destroys everything close to the star, but objects farther out can survive. What remains is a stellar graveyard, a system where planets continue to orbit a cosmic monster that bears no resemblance to the star that once warmed them. Any planet within a few astronomical units of the progenitor star is obliterated during the supernova. The explosion releases more energy in a few seconds than the star produced over its entire lifetime. The blast wave moves outward, a wall of superheated plasma that vaporizes anything in its path. Rocky planets are reduced to expanding clouds of ionized gas. Gas giants have their atmospheres stripped away, leaving behind bare cores that continue to orbit the neutron star as scorched remnants. But planets farther out can survive the initial explosion. They experience the supernova as a blinding flash of light and a surge of radiation, but the blast wave attenuates with distance. By the time it reaches the outer system, it has spread thin enough that solid bodies can endure it. These planets survive the star's death, only to face something worse: life under a magnetar. The magnetar's magnetic field extends across millions of kilometers, far enough to reach any planet in the inner or middle system. This field is not static. It rotates with the neutron star, sweeping past the planet dozens or hundreds of times per second. Each time the field sweeps by, it induces electrical currents in any conducting material on or inside the planet. For a rocky planet with an iron core, these induced currents are enormous. The planet's core acts like a giant conductor, moving through a rotating magnetic field, exactly the setup used in the electrical generators on Earth, but scaled up to planetary dimensions and driven by a magnetar's quadrillion Gauss field. The induced currents generate heat through electrical resistance, and the amount of heat is staggering. Within years or decades, the planet's core begins to melt, not from radioactive decay or residual heat from formation, but from electromagnetic induction. The temperature rises until the iron core becomes liquid, then continues rising as the magnetic field continues to pump energy into the system. Convection currents develop in the molten core, creating secondary magnetic fields that interact with the magnetar's field in complex feedback loops. The surface of the planet responds to the heating below. Volcanic activity increases. Lava flows across continents. The crust fractures as thermal expansion and contraction cycles stress the rocky layers. If the planet had oceans before the supernova, they boil away within centuries. The atmosphere thickens with volcanic gases, carbon dioxide, sulfur compounds, water vapor from the vaporized oceans. The planet transforms into a volcanic hellscape, not from proximity to a star, but from electromagnetic torture inflicted by the magnetar's rotating field. Gas giants suffer differently. A gas giant has no solid surface and no iron core, but it does have a metallic hydrogen layer deep in its interior, where pressure squeezes hydrogen into a conducting state. The magnetar's field induces currents in this layer, heating it and driving convection patterns that would not exist around a normal star. The planet's atmosphere becomes violently unstable. Storm systems larger than Earth develop and persist for centuries, driven by the internal heating rather than solar radiation. The gas giant's magnetic field, normally generated by convection in the metallic hydrogen layer, becomes entrained with the magnetar's field. The two fields interact, creating magnetic reconnection events in the space between the planet and the neutron star. These reconnection events release energy in the form of particle beams and X-ray flashes, turning the planet into a miniature version of the magnetar itself. The planet develops its own magnetosphere of tortured plasma, a bubble of electromagnetic violence surrounding a world that has become an active participant in the system's destruction. But the induced heating is not the only threat. The magnetar's starquakes release gamma-ray bursts that flood the system with hard radiation. Any planet in the beam's path receives a lethal dose with each eruption. The atmosphere is ionized. Ozone, if it exists, is destroyed. Organic molecules are broken apart by high-energy photons. If life somehow survived the supernova, it does not survive the first starquake. The radiation also affects the planet's atmospheric chemistry in permanent ways. Nitrogen and oxygen, if present, are converted into nitrogen oxides by the gamma rays. These compounds are highly reactive and corrosive. They rain down as acids, altering the surface chemistry and making the environment even more hostile. Carbon dioxide is photodissociated into carbon monoxide and oxygen, creating an atmosphere that would be toxic to any Earth-based life form. Over thousands of years, the cumulative effects of induced heating and repeated radiation bursts transform any surviving planet into something unrecognizable. Rocky worlds become volcanic wastelands with surfaces continuously reshaped by tectonic violence. Gas giants develop atmospheric chemistry that has no analogue in the solar system, driven by processes that mix thermal energy from below with radiation bombardment from above. And yet, planets continue to orbit. Gravity does not care about magnetic fields or radiation. The orbits remain stable, unchanged by the violence occurring within the planetary bodies themselves. From a distance, the system might appear normal, a neutron star with planets. But up close, every world is a monument to sustained cosmic violence, a demonstration of what happens when electromagnetic forces operate on planetary scales. The stellar graveyard is not empty. It is populated by worlds that survived one catastrophe only to endure another. They orbit a star that is no longer a star, bound by gravity to an object that tortures them with magnetic fields and radiation. These are not habitable zones. These are execution chambers operating on geological timescales, where the sentence is carried out slowly, over millennia, until nothing remains but scorched spheres of rock and metal, orbiting a neutron star that will outlive them all. The question that should concern anyone living in a galaxy with thousands of magnetars is not whether starquakes happen, but how often. Predictability would provide some measure of comfort. If starquakes followed a regular schedule, Civilizations could prepare, evacuate, or at least know when the danger window was closing. But magnetar starquakes do not follow patterns. They are fundamentally chaotic events driven by internal processes that operate on timescales we cannot predict. The data astronomers have collected over the past few decades paints a disturbing picture. Magnetars experience small bursts, brief X-ray flares lasting milliseconds, with alarming regularity. Some magnetars produce dozens of these small bursts per year. Each burst represents a minor fracture in the crust, a small adjustment as magnetic stresses redistribute themselves across the neutron star's surface. These events are not individually dangerous beyond a few hundred kilometers, but they are a constant reminder that the crust is unstable. Medium-sized starquakes, events that release energies equivalent to what the Sun produces in decades or centuries, happen every few years on active magnetars. These quakes produce X-ray and gamma-ray bursts that can be detected across thousands of light-years. If a planet happened to be in the path of one of these bursts at a distance of 1 or 2 light-years, the radiation dose would be severe enough to affect atmospheric chemistry and potentially harm surface ecosystems. Giant flares, the catastrophic events that release energies comparable to 100,000 years of solar output, are rarer. Statistical analysis of the known magnetar population suggests that each magnetar experiences 1 or 2 giant flares during its active lifetime, which lasts approximately 10,000 years. After that, the magnetic field decays, the internal stresses stabilize, and the magnetar transitions into a quieter state resembling an ordinary neutron star. But 10,000 years is a long time, and 1 or 2 giant flares per magnetar means that across a galaxy containing thousands of magnetars, giant flares are happening somewhere every few decades. The Milky Way likely experiences several magnetar giant flares per century. Most go undetected because they occur on the far side of the galaxy, or because their beams do not point toward Earth. The ones we do detect, like the December 2004 event, are the exceptions where geometry and timing aligned to make the burst visible. The unpredictability comes from the fact that starquakes are driven by the evolution of the magnetic field inside the neutron star, and this evolution is not something we can model accurately. The field is generated and sustained by currents flowing through the neutron star's interior, through layers of superfluid neutrons and superconducting protons. These materials obey quantum mechanical rules that differ fundamentally from the classical physics governing ordinary fluids and conductors. Magnetic field lines can become twisted and tangled as currents shift and evolve. The topology of the field stores energy, like winding up a spring or twisting a rubber band. When the field configuration becomes too stressed, it undergoes a reconnection event, snapping into a lower energy state and transferring the released energy into the crust as mechanical stress. The crust fractures, and a starquake occurs, but predicting when the field will reach the breaking point requires knowing the exact internal structure of the neutron star, the distribution of currents, the strength and orientation of the field at every point inside the star. We do not have this information. We cannot see inside neutron stars. We can only observe their surface emissions and infer what might be happening below. The situation is analogous to earthquake prediction on Earth, but worse. Seismologists can monitor stress accumulation along fault lines and make probabilistic forecasts about when earthquakes might occur. They have centuries of data, detailed knowledge of crustal structure, and instruments that can detect precursor signals. Even with all of that, earthquake prediction remains unreliable. Short-term forecasts are nearly impossible. For magnetars, we have none of those advantages. We cannot monitor stress accumulation inside the neutron star. We have only a few decades of observational data, covering a tiny fraction of a magnetar's active lifetime. We do not understand the internal structure well enough to build reliable models, and we have no confirmed precursor signals that would indicate an imminent starquake. Some astronomers have searched for patterns in magnetar burst sequences, hoping to find periodicity or increasing burst frequency that might signal an approaching giant flare. The data shows no clear patterns. Magnetars can be quiet for years and then suddenly erupt without warning. They can produce a flurry of small bursts that lead nowhere, or they can go from quiescence to giant flare with no intermediate activity. This unpredictability has profound implications for any civilization within the danger radius of a magnetar. You cannot plan for an event that might happen tomorrow, or might not happen for another 1,000 years. You cannot evacuate a planet based on probabilistic forecasts that are essentially random guesses. You can only live with the knowledge that the threat exists and could manifest at any moment. The statistical risk depends on the number of magnetars in your galactic neighborhood and their ages. A young magnetar, one that formed within the past few thousand years, is in its most active phase and poses the highest risk. An old magnetar, one that has been quiet for tens of thousands of years, is less dangerous but not entirely safe. The magnetic field decays slowly, and even a decaying field can produce starquakes if the internal stresses are distributed unfavourably. For Earth, the nearest known magnetar is 9,000 light-years away, far beyond the lethal radius for even a giant flare. But that is only the nearest known magnetar. Dormant magnetars that are not currently erupting would be invisible to most surveys. There could be a magnetar within 10 light-years of Earth, hidden by its quiescence. The probability of such a nearby undiscovered magnetar is low but not zero. Estimates based on stellar populations and supernova rates suggest that the odds of a magnetar existing within 10 light-years of Earth are less than 1%. Those are reassuring odds until you consider that 1% is not zero, and the consequences of being wrong are extinction level. Humanity has existed for roughly 300,000 years. Civilization has existed for roughly 10,000 years. In that time, no magnetar within lethal range has erupted and sterilized Earth. We are still here, which means either we have been lucky or there are no nearby magnetars. We do not know which, and luck, by definition, does not last forever. Somewhere in the galaxy, a magnetar is building stress in its crust right now. Magnetic field lines are twisting, currents are shifting, and the breaking point is approaching. When it arrives, a gamma-ray burst will explode outward at the speed of light, and anything in its path will have no warning and no time to react. The starquake will happen. The only question is where and when, and whether anyone will be there to witness it. The comparison between magnetars and black holes is not just about danger. It is about the nature of that danger, and which object represents a greater existential threat to anything living nearby. Black holes have dominated popular imagination as the ultimate cosmic predators, but a systematic analysis reveals that magnetars are worse in nearly every measurable way. Start with the threat radius. With a mass between 3 and 20 times that of the Sun, has an event horizon radius measured in kilometers. For a 10 solar mass black hole, the Schwarzschild radius is roughly 30 kilometers. This is the point of no return, the boundary where escape velocity equals the speed of light. Inside this radius, nothing survives. Outside it, survival is possible if you maintain a stable orbit. The tidal forces near a black hole extend somewhat farther. The tidal radius, where gravitational gradient becomes strong enough to tear apart objects through differential forces, is roughly a few hundred kilometers for a stellar mass black hole. A human body would be spaghettified at this distance, stretched along the radial direction and compressed perpendicular to it by tidal forces that overcome molecular bonds. But beyond the tidal radius, a black hole becomes manageable. At a distance of 1,000 kilometers, roughly 30 times the event horizon radius, the gravitational field is strong but not immediately lethal. You could orbit at this distance indefinitely. At 10,000 kilometers, the gravity is comparable to what you would experience near a white dwarf star. At 100,000 kilometers, roughly 3 times the distance from Earth to the Moon, the black hole's gravity is weaker than Earth's surface gravity. You're effectively safe. Now consider a magnetar. The magnetic field strength at the surface is 10 to the 15th Gauss. At 1,000 kilometers, the field drops to approximately 1 billion Gauss due to the inverse cube law governing magnetic dipole fields. This is still strong enough to polarize the quantum vacuum, distort atoms, and induce lethal electrical currents in any conducting material. You cannot survive at 1,000 kilometers from a magnetar any more than you could survive at that distance from a black hole. But the magnetar's danger does not stop there. The gamma ray bursts from starquakes propagate outward at the speed of light, maintaining lethal intensity across distances measured in light years, not kilometers. A giant flare can deliver a biologically significant radiation dose at 10 light-years distance. 10 light-years is 95 trillion kilometers. The magnetar's effective kill radius is roughly 1 trillion times larger than the black hole's tidal radius. This difference in scale fundamentally changes the strategic threat assessment. A black hole is a localized hazard. If you know where it is, you can avoid it. If your civilization's home system does not contain a black hole, you're safe from black holes, unless one happens to pass through your neighborhood, an event so statistically improbable that it can be ignored for practical purposes. A magnetar is a regional hazard. If one exists within 10 light-years of your home system, you are in the danger zone regardless of whether it is in your system or a neighbouring one. The threat extends across multiple star systems simultaneously. A single magnetar can threaten dozens of stars and hundreds of planets within its lethal radius. The predictability factor also favours black holes. A black hole's behaviour is deterministic. Its gravity follows the equations of general relativity with extraordinary precision. You can calculate orbits, predict trajectories, and plan navigation with confidence. The black hole does not suddenly change its gravitational field or emit unexpected bursts of radiation. It is consistent, and consistency allows for planning and mitigation. Magnetars are chaotic. Starquakes happen without warning. The intervals between eruptions vary unpredictably from years to decades. You cannot predict when the next burst will occur or how powerful it will be. This unpredictability makes defense impossible. You cannot evacuate based on forecasts that amount to random guesses. You cannot shield a planet from a gamma-ray burst you did not know was coming. Black holes also have the advantage of being relatively easy to detect. An isolated black hole is invisible, but black holes in binary systems or those actively accreting matter produce distinctive X-ray emissions as in falling material heats to millions of degrees in the accretion disk. These emissions are bright and persistent, making the black hole's location obvious to any civilization with X-ray telescopes. Magnetars can hide. A dormant magnetar that has not erupted in centuries emits only faint thermal X-rays from its cooling surface. It looks nearly identical to an ordinary neutron star unless you can measure its magnetic field active emission phases. Your civilization could remain undetected until it erupts, at which point the warning time is zero because the gamma rays travel at light speed. The nature of the destruction also differs. A black hole kills through gravity. If you fall past the event horizon, you are compressed and torn apart by tidal forces, but the process is localized to you and whatever matter accompanied you across the boundary. The black hole does not reach out and destroy your home planet. It does not sterilize your star system. It simply removes whatever crosses the point of no return. A magnetar kills through radiation. A gamma-ray burst does not discriminate. It floods entire star systems, hitting every planet in the beam's path simultaneously. The radiation ionizes atmospheres, destroys ozone layers, and delivers doses that cause ecological collapse. The destruction is not localized to objects that ventured too close. It is broadcast across light years, affecting worlds that never approached the magnetar and had no way to avoid the danger. From an existential risk perspective, the magnetar is worse because it threatens more targets simultaneously and offers no realistic defense. A civilization can avoid black holes by not going near them. A civilization cannot avoid a magnetar's gamma-ray burst if it lives within the danger radius. The only defense is not being there when the starquake happens, which requires either knowing the magnetar's location and evacuating preemptively, or having the capability to relocate entire planetary populations on short notice. Neither option is practical for most conceivable civilizations. The final consideration is frequency and distribution. Stellar mass black holes are relatively common in the galaxy, with an estimated 100 million to 1 billion scattered throughout the Milky Way. But they are also diffuse, spread across a volume of space large enough that the average distance between black holes is hundreds of light-years. The odds of a star system being within dangerous proximity to a black hole are vanishingly small. Magnetars are rarer, with perhaps 10,000 to 100,000 in the galaxy at any given time. But their danger radius is so much larger that the probability of being within lethal range is comparable to, or greater than, the probability of being near a black hole. A magnetar at 10 light-years is as dangerous as a black hole at 10 kilometers, but there are far more star systems within 10 light-years of a given magnetar than there are objects within 10 kilometers of a given black hole. When you combine all factors, threat radius, unpredictability, detectability, and the nature of destruction, magnetars emerge as the more dangerous object. They are the cosmic equivalent of landmines scattered throughout the galaxy, invisible until they detonate, lethal across distances that encompass multiple star systems, and completely indifferent to whether anyone is paying attention. Black holes are famous, but magnetars are the real killers. They just do not have the same public relations.